This video is a walkthrough of answering an exam question. The only way to learn how to answer questions is by actually answering questions. It doesn't work to just passively absorb the ideas, you have to do it yourself. So as I go through this question, I'm going to put in breaks where I say, now pause the video, and you should go and work out your own answer with pen and paper. Then you can resume and see how your answer compares to mine. You'll need the question in front of you. Click on the link underneath this video and it'll take you to the question PDF. So let's get started. I don't bother reading the text of the question until I know what it is I need to actually do. I'd start off by skimming through everything, but just looking for keywords. For here I want to know what's the topic and what section of notes is likely to be relevant. Here, skimming through, there's a whole load of specifics about a model, but the generic keywords that I see are log likelihood, maximum likelihood estimator, and pseudocode for finding maximum likelihood estimators. So that tells me it's something to do with likelihood and maximum likelihood estimation and numerical optimization. I may also see the y1 ... and that may put me in the mindset of either generative models or supervised models. Next, I'll look for question words. Question tells me find an expression for log likelihood and give pseudocode. There's no point trying to understand the exact model until we know what it is we need to do with it. Finally, I'll think through the course. I know what it is I have to do, I know roughly the keywords, so I'll think through which sections of the notes are relevant to the material here. To answer a question about likelihood and to do modelling, we need to be familiar with the notation for random variables. We can see it's being used here in the question. The question refers to a normal distribution. I ought to remember that. I ought to think through this section of the notes on finding likelihood. What were the tricks we used there? We talked about independence. We talked about deriving the likelihood from the CDF. We talked about the likelihood of a data set. Then the section of the notes on numerical optimization, what did we cover there? We covered how to use the SciPy function to optimize, and mainly we covered how to transform parameters to make your question optimizable. So these are the sorts of things that should be floating around in my head before I actually get started. Part 1. The question asks us, find an expression for the log likelihood. Let's just write out something generic about likelihoods. I'm going to write out the likelihood. It's a function of the observed data, semicolon, the parameters. Stop now and read through the question and look at all the symbols in the question and figure out, are they about observed data or are they parameters? If parameters, are they known or unknown? The observed data, we've got y1 up to yn. The question also tells us about big Y, I. That's the distribution, the random variable from which the observations are made. And the parameters in the question, there's obviously the theta, which is an unknown parameter. The question's all about trying to estimate theta. The other symbols we see, there's an epsilon, which is known. We're told so in the question. There's an n, which is known. We're not explicitly told that, but we're given a data set y1 up to yn, so n is just the length of the data we're given. And the other symbol in the question is xi, and we're given a formula for xi. Xi is a function of theta. What's the question asking us for? We want log likelihood of y1 up to yn as a function of theta. And we're told in the question that yi is distributed like xi plus normal of naught epsilon squared. The job of the question is to bridge these two, go from what we're told to what we want to find out. This is a point to pause and ask yourself, what would you do next? How much of the algebra can you go through? First thing I'm going to do is I'm going to start with what we want. And I'm going to break it down, as we've seen so many times in the notes, as the sum over I log likelihood of yi given the unknown parameter theta. I'm going to write assuming independence. In all the examples in the notes we've done this, we've assumed independent observations. We're not explicitly told in the question that the observations are independent, but in the section of notes where we talked about notation for random variables, we said if we're not explicitly told that the random variables written out in the question are dependent, we should just assume they're independent. There's nothing in the question here which says assume they're dependent, assume they're related to each other, other than via the unknown parameter theta. So we will go ahead and assume independence, and we'll write down the assumption we're making. The other thing I'm going to do here is I'm going to just say little yi is drawn from distribution big yi. Okay, so next step, we need to work out what is this distribution of capital YI. We're told it in maths notation, we need it in likelihood notation. Next thing I'm going to do is I'm going to just rewrite this slightly as normal with mean xi and variance epsilon squared. This is a standard thing to do with normal distributions. It's referred to as linearity of the normal distribution. If you take a normal, add a constant, i.e. add a non-random value, then you end up with another normal. Now this is a very standard random variable. You should just remember off by heart what its likelihood function is. When I write out likelihood functions, I tend to write them out at a generic point, little y, where I'm asking what's the density at this point. So in this formula I've got a generic point, little y, where I'm asking what's the density, but I'm asking about the density of the random variable big yi, and big yi is parameterized by xi, so that's why there's an I here as well. Okay, so we've got the likelihood for each individual observation. Let's just stick that into the formula here. Again, I'm being really careful. Here we're talking about a specific observation, little yi, and so I'm using that. I'm not just blindly copying out the formula I had on the right, which had a plain unadorned little y. Just a tiny bit more algebra. So, this answers the question, we've found the likelihood. Well, not really, or not very convincingly. The question asks us, find the likelihood of y1 up to yn as a function of theta. And our answer here doesn't have theta at all, which seems a bit worrying until we realize, hey, hold on, xi is just a function of theta. It doesn't do any harm to write it in explicitly as a function of theta. If we don't do that, we're likely to be led astray when we try and do maximum likelihood estimation for theta. So let's just write out actually what xi is. Xi is a function of theta, tells us in the question what that function is. And I'm going to just rewrite that using the indicator notation. Indicator that I is above theta. Just when I'm doing algebra, I prefer to work with indicator notations rather than case statements all over the place. So if we just stick that in here, we get minus n on 2 log 2 pi epsilon squared minus 1 on 2 epsilon squared sum of yi minus the indicator that I is above theta all squared. Okay, that answers the question. Next, give pseudocode for finding the maximum likelihood estimator theta hat. Let's just do the obvious thing. We'll define a function, let's say def log like of theta, return this expression which we've just derived. And then we could use scipy.fmin to minimize minus log likelihood function with some initial guess. The question doesn't tell us what the data set actually is, so we can't really make the initial guess. But then we think back, hold on, what did we cover in the section of the notes on numerical optimization? The big topic there was, do we need to transform? So let's think again, what's the domain that we're trying to optimize over? Reading the question, it actually tells us that theta has to be in a discrete set. Okay, so what we just wrote down here is rubbish. Scipy.fmin is all about optimizing over a continuous random variable, whereas we want to optimize over a discrete random variable. That's actually much simpler to do. We want to optimize over theta in this discrete set, so all I'm going to do is I'm going to use Python to iterate over it exhaustively. Let's say let vals equal list comprehension. I'm going to compute log likelihood of theta, and I'm going to store the associated value theta for theta in the range that we're interested in. And then I'll pick out the maximum item in this list. This is just a standard Python idiom. If I have a list of pairs and I choose the maximum, it will sort them lexicographically. In other words, it will return the pair where the log likelihood is highest, but I get the pair back, so I know the value of theta where the log likelihood is highest. And that's what I'm extracting with this code here. You don't have to use this sort of magic. And you can see in the answers I'm very sloppy with my pseudocode. I'm not trying to write precise Python. For an exam, you don't need to write precise Python. You just need to give instructions to the extent that someone who's a normal first-year undergraduate computer scientist would probably be able to understand them. Okay, we've answered the question. Here's part B. Let's do the usual sort of scanning through the question as a whole to see what we need. First, skim read the entire question for keywords. What's the topic? Keywords I see here, cumulative distribution function. I can see it written out in text and also in maths notation. Density, calculate the density. Dataset, fit unknown parameters using numerical optimization. Next, look for question words. Give formulae, calculate, explain how to fit unknown parameters. These give formulae and calculate, that's just maths. Explain how to fit, so I'm thinking pseudocode for optimizing. Next, think through the course. What topics are relevant? This is a question which is talking about cumulative distributions and densities, which we covered in the section on likelihood. And specifically, we had this diagram which led to calculating the likelihood via the cumulative distribution function. There's also reference to numerical optimization. In that section of the notes, there was a code snippet, and there was a whole chunk about transforming parameters to make them easily optimizable. So we can get started. We're asked to give formulae for these two probabilities. When you see a pair of probabilities like this, your mind should immediately go to the law of total probability, which says that if we want to compute the probability of an event like this one, big X less than or equal to little x, we can decompose it into all the ways that it might have happened. We're told the distribution of k, and given k, we're told the distribution of the random variable x. So we have to solve for these two probabilities. This is time for you to stop and think and see where you would go yourself. First thing I would do is I just substitute in what we know. Conditional on the value of big K, we know that big X has this specific normal distribution with given mean and variance. In this equation I've just written, I've written mu subscript little k and sigma subscript little k because we are conditioning on a specific value, big K equals to little k. The question pretty much tells us what to do here. We're after the cumulative distribution function of a normal. The question tells us, give your answers in terms of cumulative distribution function for a normal, namely this big phi. So there's nothing more we can do here. For the second one, well, this bit's easy. We've already worked out the first part of the law of total probability. We just need the other term, probability that big K equals little k. So let's just read the question, see if we can dig that up. We're told probability of big K equals little k is P subscript k. So the answer just writes itself. Good. Part 2, we're asked for the density of the random variable x, and we've just been told to produce the cumulative distribution function, so that's a pretty good hint. We're meant to differentiate the CDF to get the density. This is time for you to try it out yourself, see where you go. I'm just going to write out exactly what it is that we're trying to differentiate. We want to differentiate this sum over k that we just found in the last part. I've rearranged it slightly. We're left with this nasty looking thing, d by dx, capital phi of x. So what do we do with that? What the question's doing here, it's really asking us to think what that definition of big phi means. What is big phi? Big phi is just the cumulative distribution function for a normal. Big phi sub mu comma sigma of x is probability that given normal takes a value less than or equal to little x. So what does that tell us its derivative must be? Well, this is exactly what we're using. We're using the fact that the derivative of CDF is PDF. If you differentiate it, you must simply get the density function of a normal distribution. I'm writing it out here in the likelihood notation, PR subscript normal mu of sigma squared random variable. That's the density evaluated at some arbitrary point little x. So we can just write out the density of a normal distribution. This is a density which you ought to know and memorize. We get this sum here. Next, part 3. The question says, given a dataset x1 up to xn, explain how to fit the unknown parameters using numerical optimization. Fit, in the context of this course, just means find a maximum likelihood estimator. And likelihood is the likelihood of the observed data given the parameters. Let's just run through the question, remind ourselves what the observed data is and what the observed parameters are. The observed data is little 1 up to little xn, the data set that we're given. It doesn't tell us explicitly, but this is what the question implies. We're going to assume that those values are sampled from the distribution capital X. And the parameters in the question tells us literally in the text, here p1 up to pm, mu1 up to mu_m, sigma1 up to sigma_m are unknown parameters. I always like to start these fitting questions in this way. I write down what's all the observed data and what are all the parameters. It's the cardinal rule of maximum likelihood estimation. You absolutely have to include every single parameter which could influence the data, and you ought to use every single piece of data, because if you don't, you're throwing away information. Our goal, we're doing maximum likelihood estimation. We want to maximize the likelihood of the observed data, or let's write it, we want to maximize the log of the likelihood of the observed data over the unknown parameters. This is time to stop and think and ask yourself, how would you go about maximizing this quantity? First thing I'd do is I'd try and work out a little bit about this likelihood function that we're interested in. We're interested in the likelihood of the full dataset x1 up to xn. What we've done in pretty much every single example in the course is we've assumed that this is an independent sample from a distribution. I'm going to assume that all of the xi's are sampled independently. It doesn't tell us that literally in the question, but we're sort of meant to take it for granted if we're treating this as an exercise in generative modelling. So, if the xi are all independent, then the likelihood is the product of terms for each of the individual xi. Therefore, the log likelihood is the sum of the log likelihoods of each of the individual elements. And I'm writing out explicitly assuming independence. That's an assumption I'm making which wasn't stated in the question, so I better write it down. What makes this thing tricky, though, is that we're trying to do a constrained optimization. We're not free to choose totally arbitrary parameters p and sigma. We've got to choose p to be a probability vector. We've got to choose sigmas to be positive numbers. So how do we optimize over a constrained domain? There's time for you to stop and think and figure out how you would implement this optimization. The trick we learnt in the beginning of the course, the section on numerical optimization, is that we should transform the parameters. There are two transformations that we used in that section of the course. We used the softmax transform and we used a simple exponential transform. The softmax transform is a good way to produce a probability vector, i.e. a set of numbers between 0 and 1 that sum to 1. And then the simple exponential transform is a way to ensure that we have positive numbers. So what we're actually going to do is we'll optimize this function over, let's call them s and tau, and the same u as before. And these will all be parameter vectors, each of them m-dimensional. And we're going to apply the following transformations. I'll use the softmax transform to turn the sk into a pk. The exponential ensures that the p's are all positive and the normalization ensures they sum to 1. And I'm going to simply let sigma k equal e to the tau k to force sigma k to be positive. Now it's easy to do the optimization. It's an unconstrained optimization over s, mu and tau, so we can just solve it using scipy.optimize.fmin. Is a good practice. Whenever we call optimize, we should always enter a sane initial guess. We don't know what the data is here. Here's a plausible thing to do. The initial guess should be chosen by looking at a histogram of the dataset. That's what we might say. If the dataset looks like it's got two clusters, stick the mu1 and mu2 and the sigma1 and sigma2 to capture where those two clusters are. Let's just look over the question as a whole, both parts. We've been through the three guidelines about how to approach a question. I'm going to add on two more. Read the whole question. What's the theme? Generally, the examiner has some theme or idea in mind when they set the entire question. Possibly it's leading up to something, possibly later parts build on earlier parts, possibly there are two parts which give different views of the same idea. The examiner normally has something of this sort in mind, and it's good to just review what you've done to ask, maybe the examiner's trying to get at something and I've missed it. Here, both parts of the question are certainly both about maximum likelihood estimation. One of them was a slightly weird discrete optimization. The other one was the bog standard optimization of the sort we've done in the course. So it looks to me like this is a question with two different views of what maximum likelihood estimation is. It's basically a question about putting together probability models and fitting them. So I don't think there's anything more to it than that. Finally, seems silly to mention it, double check you've answered all the parts. There are always students who just forget to answer one of the question words. Don't lose marks when you don't have to.